Okay, so last time I have introduced a new basis of these elementary symmetric polynomials. So let's briefly summarize things. So if we have a partition I1 all the way up to IR, a partition of some number k, and we look at polynomials in at least k variables, so let's say in n variables, then we have looked at these polynomials t1 to the power I1 all the way up to the power IR. So that's a polynomial in the variables t1 up to tn. And now we commute over all. So we replace the tuple 1 to r by all possible tuples, r tuples in 1 to n. So we summarize this way. That gives us a symmetric polynomial in the t's, and we express this in terms of elementary symmetric polynomials. So we write this as si of sigma1 all the way up to. Okay. So this defines polynomials Si. Now, if we have a Chern class, which looks like this, some Chern class, or let's say go on to n, or Chern class for a bundle over a manifold M, then we can take these Chern classes and insert them in this polynomial Si. So that gives us a new homology class, which I abbreviate as Si of C. So that's also a new even homology class of M. And we can integrate it, provided it has the proper degree. So Si of C applied to M is my notation for taking this class and integrating it. And this gives me then. Okay, and for this to make sense, this must be a complex manifold of dimension k. And this is then a partition of k as stated here. If this is a partition of some other number, of course, degrees don't match, and we get just 0. All right. And one corollary of what we did last time is now the following. If we look at the product of two manifolds, one of dimension n, one of dimension n, and to compute this number for the product manifold, so this characteristic number coming from the Chern class, then this can be expressed in terms of such numbers of factors by summing over all divisions of I into subpartitions, where J is a partition of M, K partition of, well, this is now a different, this is not, that was a generic, and now we have these specific manifolds of partition of M, and we have Sj C of M times Sk C of M. And we had a similar formula for general bundles here, where we have a direct sum of two bundles. So what do we call this? Let's briefly sketch the proof once more. So this is always referring to the tangent bundle here. So C here is the Chern class, the tangent bundle. It's a complex manifold, so that's a complex vector bundle. And if we have a product of such two such manifolds, then the tangent bundle is obtained from the tangent bundle of the first factor, pulling it back from M to the product, plus the tangent bundle of the second factor, also pulling it back from the second factor. So that's what we have, and then we can apply this sum formula that we proved last time. So that means Si of C over to M plus N is Si of C of the sum bundle. Integrated over the product. And here we had this formula last time that this is given by such a sum of Sk of this first bundle, joint parts of the first bundle, integrated over the first factor. Let's say together times S. So it's Sj of the first one times Sk of the second one. And the whole thing needs to be integrated. That's the cup product. And so that's what we proved last time. And now we have a cup product. Here I can pull out the T star M, here I can pull out the T star N. If I have a product, something T star times T N star integrated over the product manifold, that is of course the same thing as integrating this one over M times this one over M. It's like the Fubini integration. And we get some splittings, and then we have Sj of C M times Sk of C N. And now we can add these additional conditions here, because these integrals give us non-zero values only if this is a partition of the dimension of this manifold. That is a partition of that. Otherwise, these sums in general they occur, but they will give you zero here. This after integration. So this is why you can just add that. This is n-dimensional and k-dimensional because n-dimensional. Yeah, so when I write C here, I always mean the C of the tangent bundle, which is inserted. So that's this understood in this notation. Yeah, maybe I should be more specific here. I should write C of, and that's the definition. Okay, so we have that, and in case, for a particular special case, we looked at that when this partition consists only of one element, as a triple partition of K into just K. Then we saw that if a manifold is a product, then this thing must give us zero. And we computed it for projective spaces, and it gave us something non-zero. So from this we could conclude that the projective spaces cannot be split as products into factors. Okay, now here's the proposition that I'm really after. It says this. So let's start with manifolds M1 all the way up to MQ to be compact, complex manifolds dimension complex dimension J. And And let's also assume that this invariant, which we get from the sort of trivial partition, which just partitions J into itself, that then this invariant of Mj is always non-zero for J. Let's assume that. For example, it could be projective spaces. Yeah? Could be CP1, CP2, and so forth. That would be an example of the situation. And the conclusion is now that the matrix, which we get by looking at all Chern numbers of all possible products where we so that things fit. So the J has to be a partition of the same number as the I here, so that we can get something non-trivial here. So, and we look at the matrix of these numbers where I and J range over all partitions of Q. So I, this is partition here, and J, this partition there, they range over all partitions of Q. And this matrix that we get is a square matrix, so this is non-singular. Okay, so we are looking at all kinds of products here as manifolds and all kinds of their Chern numbers. And we write this in the matrix, and I'm claiming this matrix is non-singular. So let's see, let's look at an example. A very simple one. So in this case, Q is equal to 2. My first manifold is as enhanced CP1, and the second one is CP2. And so we have the right dimension. And does anyone remember the values of these numbers? We computed them last time for projective spaces. One more than the complex dimension, right? So I mean, so this one, S1 of CP1 gives us 2, S2 of CP2 gives us 3, and so forth. So in any case, they're non-zero. So, and by the proposition, this matrix should be non-singular then. So let's compute the matrix to see how it looks in a concrete example. Right, so what partitions do we have? So what's the size of the matrix? We need to look at partitions of 2. They are not terribly many, right? So partitions of 2 we can write 2 as 1 plus 1, or we can 2 write as 2. These are the two options. So that's a 2 by 2 matrix. And now we have to compute these entries here. So let's see. And so let's so we have to, what do we have to insert? If the partition for this, if this partition is the partition 2, then we have to insert CP2 here. If the partition is 1, 1, we have to insert CP1 times CP1. So we need to have the Chern numbers of CP2 and of CP1 times CP1. So let's see. Remember the Chern class of CP2. This we know, that's 1 plus this generator of second homology to the third power. And if we spell it out, then I get 1 plus 3 times A plus 3 times A squared, and A cubed is already 0. So that's the Chern class of CP2. And okay, so this gives us, in particular, that's the second Chern class here. So if I look at the second Chern class of CP2 and integrate it over CP2, then I have to take this Chern class and integrate it over CP2, and the appropriate power of A integrated over CP2 gave us 1. So this integrating this gives us 1, so that we get the value 3 here. So this gives us the value 3. Now the first Chern class of CP1 squared is, the first Chern class is this one, so this will be 3 times A squared, so another way 9 times A squared, and so if I now integrate it, C1, this Chern number of CP2 is 9. So that's the value 9. Okay. That should be CP2, sorry. I'm sorry. Yeah. Now let's look at CP1, and in fact what we need is not CP1 itself, but CP1 times itself. We know how the Chern class behaves under Cartesian products from the exercises. That is CP1, Cartesian product with the cohomology class CP1. And so this one is given as 1 plus A squared now. Now it's CP1 times, and here I have to give the generator a different name because it's a second copy. So let me write this as 1 plus A prime squared. A prime is the corresponding generator of the second copy of CP1. And so this is 1 plus 2A times 1 plus 2A prime. And let's multiply this out. 1 times 1 is 1. Then we have 2A times 1 plus 1 times 2A prime. So we have 2, 1 times A prime plus A times 1. And then we also have this times that one, which is 4A times A prime. That's what we get for that Chern class. And so if we look at the second Chern class, this is given by that guy, and integrate it over CP1 times CP1. And of course this term again integrates to 1, because we first integrate that one over CP1, which gives us 1 times that one over CP1, which gives us 1. 1 times 1 is 1. So that means this integration gives 1, so we are left with 3 factor 4. And finally, C1 of this product. So here, so this is C1, we have to now square this first. So the Chern class before integration, C1 of CP1 times CP1 squared. I have to square this one. This gives me 2 times 2 is 4. And I have this guy squared, but that means gives me 1 times A prime squared, which is 0. And similarly, if I square that one, I get A squared times 1, which is also 0. A squared is 0. So only the mixed terms contribute, and those I have 2 times. And this times that is of course nothing but A times A prime. So what we actually get is 8A times A prime. And if we integrate this over the manifold, then we get 8. Good. So the matrix in this case is given by, so here let's start with 1, 1, the 1, 1 terms on the left, and let's start with the CP1. So then I have 8, that's this term, and the other C1, 1 term is where it is here, that's 9. And then I have the C2 terms. The C2 term of the product is 4. And the C2 term of CP2 is 3. So that's the matrix. And indeed, the determinant of this matrix A set is 24 minus 4 times 9 is 36. So that's minus 12, which is 0. But from looking at the matrix, one has no clue why this statement should be true. It turns out to be correct in this example, but there is no structure that we see or anything from which we might conclude that this matrix is not singular. So how do we prove that? All right, so maybe we can erase the example now. And in fact, in order to prove it, we do not directly look at this matrix. Instead, we look at the matrix, which is not given directly by the Chern numbers of the products, but rather, so we take the product, so this is not changed. But instead of looking at the Chern numbers directly, we look at the SIs of Chern, where I runs over all these partitions. And in fact, remember, the elementary symmetric polynomials, they form a basis of the symmetric polynomials, but these ones do too. So we can express these terms as linear combinations of those, and by conversely. That means if we compare these two matrices, they are related by the multiplication with a matrix, and that matrix is non-singular because we can solve for both sides. In other words, this matrix is non-singular if and only if that matrix is non-singular. So that's why we work with this matrix now. Good. Well, what can we say here? Here the situation is somewhat better because we have this formula that I recalled in the beginning. If I have SI, so remember SI, when I said, I wrote down, if I have a product, then this can be written as the sum over all partitions of this, or subdivisions of this partition of the individual factors. And in fact, doing a simple induction, we can generalize this to more than 2 factors. So let's do that, or also directly prove it for more than 2 factors. So instead, I take more than 2 factors. Then I have the corresponding formula here too, and I have to subdivide then this partition into S subterms. So I have to write this as I1 all the way up to IS equals I. Then I have I1 here, MJ here, and so on. S of MJS here, where we subdivide the partition to these partitions. So that's the obvious generalization. The proof, you could prove it directly, so it would be the same proof as for 2 factors, just the notation is more clumsy, or you do an induction if you want. Now, what can we say now about, what can we conclude from this observation? Well, when can this actually be non-zero? In order to such a term to contribute, all the factors must be non-zero. Now, when can these factors be non-zero? In order for these factors to be non-zero, we must have that the I1 really is a subdivision of the complex dimension of mj1, right? And similarly for the other factors, because if the degree and the dimension here don't fit, then this integral gives us 0. So the whole term can only contribute if the I1 is really a subdivision of J1 and the IS is a subdivision of JS, because these are the dimensions of these manifolds. In other words, this term can only contribute, gives us only something non-zero, really, if the I is a refinement of the index J. Because only then I can subdivide I in such a way that the dimensions fit. So that is non-zero, or is equal to 0, unless I is a refinement of J. And that means in this matrix, lots of entries are actually 0. Namely, whenever the I is not a refinement of this partition J, then it's 0. Now, what we do, choose an order on the set of partitions of Q such that I is less than or equal, with respect to this order, less than or equal to I prime if I is a refinement of I prime. So you choose an order and then you can pick the partitions, and then the next partition is put in the order in such a way that whenever something is a refinement, it will satisfy this relation. And if you do it, and now if you write down the matrix with this order of these indices, then you observe that the matrix that we get here is triangular. Because you get something non-zero only if one of the indices is less than or equal to the other one. So therefore, matrix is triangular. And that's good, because now we can easily read off whether or not the matrix is singular by looking at the diagonal entries. So let's take a look at the diagonal entries. So this is when both indices coincide. So we have Si of C applied to the manifold Mi1 cross and so forth cross Mi R. And again, you see by this formula, now there's only one possibility where the thing contributes, namely if you just apply the I1 to that factor and so on. So from this formula, what we see is that gives us Si1 applied to Mi1 times SIR applied to R. And now we have this assumption that these numbers are all non-zero. These numbers that occur here, and so the product is non-zero. So the diagonal entries of this matrix are non-zero, and this shows matrix is non-singular. Okay. And to see this was the main reason for introducing this new basis of elementary symmetric polynomials. Good. Yeah, well, you can complete this in any way to complete order, right? So, of course, if you say this, first you define this relation. So the question is, you define this relation. I'm not saying if and only if here, right? I'm only saying if here. So first you fix this this relation in case you have a refinement, and then you have to think a bit that you can complete this to a complete order. But that's not hard to do. I'm not saying if and only if here. All right. So now the same playing game can be played with Conjugaten classes instead of germ classes, and then we have to look at oriented manifolds rather than complex manifolds. The same analogously, we have the corresponding proposition where we have from 1 all the way up to MQ compact oriented manifold, compact oriented manifold, differentiable manifolds with dimension. Now I have to take the dimension. In the previous case, I had to take complex dimension j, so 2 times the real dimension. Now I have to take 4 times the real, the real dimension is 4 times j, and the corresponding quantities for the Pontryagin class applied to these manifolds is non-zero, and then the matrix obtained from Pontryagin numbers applied to this product manifolds this matrix is non-singular. It's exactly the same. All right, and now we can return to our Foucauldian ring. Namely, let's recall this theorem by Tom that I have stated without proof, which gives us the structure of the oriented cobordism ring in dimensions divisible by 4. And the statement is now omega 4k, that's an abelian group, remember. So that's free, as a free Z module with basis given by a product of complex projective spaces. They have to the even dimension must be, the real dimension must be divisible by 4, so we have to take complex dimensions which are even here. Where these partitions, this ranges over all partitions of K. So the corresponding product of complex projective spaces give us a represented basis. This basis represented by these manifolds. And I had announced that I prove only one part of it, namely the linear independence. And this is now basically a consequence of this proposition. Proof of linear independence of these cobordism classes. Namely, we remember that the Pontryagin numbers, EI, applied to any 4K manifold or cobordism class of that. So these Montiaga numbers, they are well defined on cobordism classes. They give us numbers as results, and I mentioned already that these, we proved it, that these are group homomorphisms. Well-defined group homomorphisms. And now we know if we apply these group homomorphisms to these particular manifolds here, right? So the theorem can be applied with this choice of manifolds. Then we get a non-singular matrix. Okay, so the PI applied to these classes here, represented by these projective spaces. So this gives a non-singular matrix, and therefore there can be no non-trivial linear relation between those. Because if there was if this was linear independent, then there would be a non-trivial linear relation between these ones, and then we would have corresponding relation between the rows of this matrix, and it would be a singular matrix. So therefore we have linear independence. Okay. So we could also prove the fact that these manifolds generate everything, so that they are really a basis. But then I would have to do even more preparation, Tom construction, etc., which I did not do, because we have still a few other things to discuss. All right. Now we have everything available, almost, in order to prove Hirzebruch signature theorem. So let's do that next. So let me briefly recall what the Hirzebruch signature theorem is about. It's about, so what's the signature? The signature of a quadratic form, and the quadratic form is defined by cohomology of the manifold. So we have a manifold, compact, oriented, differentiable manifold, dimension divisible by 4. It's 4K. And now there's a quadratic or bilinear form on the second homology. So it's a half of the dimension. That's 2K homology, half of the dimension. Going to real numbers up. And this is given by, take a homology class here, omega, take a homology class there, beta, and map this pair of homology classes to the following number. Yeah, well, take the wedge product of the two differential forms, which gives us a 4K form on the manifold, and the manifold is oriented, so I can integrate. Gives me a number. Now this is well defined. It depends only on the homology classes of these two forms, and it's also a symmetric bilinear form because both these degrees are even. So if I interchange the wedge product, I do not get a sign. So that's a symmetric bilinear form. So if the dimension of M was even but not divisible by 4, then we would get a skew symmetric form. Okay, anyway, and any bilinear form on a finite dimensional real vector space has a signature. It's actually a non-degenerate symmetrical linear form here. We haven't proved that. That's a consequence of non-parity duality. Non-parity duality basically is the statement that this is a non-general form. But anyway, the number of positive and negative minus negative eigenvalues gives us a signature. And this is called the signature of the manifold N. So the signature of the manifold is by definition the signature of this bilinear form. Maybe I call this the Poincaré map. Capital P. Poincaré form, bilinear form. So that's the signature of the manifold. So that's an important topological invariant for manifolds divisible by 4. Compact. And let's recall Hirzebruch's signature theorem. It's similar to the Gauss-Bonnet-Chern theorem, where we express a topological quantity, namely the Euler number, by certain characteristic classes, namely the Euler form by Pfaffin of curvature. Here we express the signature of the manifold in terms of a certain characteristic class, namely, so under this assumption, the signature of M is given by, you take a certain class coming from the tangent bundle, the L class, integrate it over the manifold. This gives us a number. And what is that thing? Where L of Tm is the multiplicative class for the Pontryagin class of the tangent bundle, and the power series little L of T being given by square root of T on hyperbolic tangent of square root of T. So this is a formula, well, that's a power series on T with rational coefficients. So remember, the square root should not confuse you, because this is an odd power series. So if you divide by this, you get an even power series, and an even power series in square root of T is a power series of T. So this is how it's to be understood. Okay, so then we have discussed these multiplicative classes at length, and I'm claiming if I take this particular class with a hyperbolic tangent, integrate that over the manifold, I get the signature which I've just described here. And one might wonder, why should these things be related at all, right? And I'm going to give you the proof, but before I prove it, we need to know a little bit about the signature. So let me formulate this as theorem. So the signature has the following properties. So the signature of a compact oriented 4K manifold has the following properties. So firstly, if we look at the signature of the disjoint union of two manifolds, then this is the sum of the individual signatures. And why is that? Well, what is the cohomology of the disjoint union? So if you look at the 2K cohomology of the disjoint union, this is represented by forms, and of course a form is given just by the form restricted to one and to the second thing. And so that we have a natural isomorphism with the cohomology on M1 plus the cohomology on M2, which is simply given by restricting to M1 and M2. Right? If you take a restrict to M1 or to M2, this gives us something here or somewhere. You can go back. If you have cohomology class here represented by a form on M1 and something here, you put it together as a form of the disjoint union representing something here. So there's this canonical isomorphism identity. And now, not only in degree 2k, any degree of course. But here we are interested in degree 2k because this is where the Poincaré bilinear form lives. And now, if we look at the Poincaré bilinear form for this disjoint union, then with respect to the splitting, this is a 2 by 2 matrix, right? And if I just restrict to M1 everything, then I just get the Poincaré map of M1. Because I have to wedge the things and integrate over M1. And similarly on M2. And if I have something on M1 and the second argument is on M2, then this means the first thing is 0 on M2, the other thing is 0 on M1. If I wedge the two things, then it's 0 everywhere, and if I integrate it, I get 0. So I have 0 here, I have 0 here. And now, if we look at the signature, obviously the signature of this one is the signature of this one plus the signature of that one. The signature of M1 is just union, M2 is the sum of the individual signatures. Alright. The second property is what happens if I take the product to such manifolds. So both manifolds should be manifolds of dimension divisible by 4, compact oriented. Then the product is again dimension divisible by 4, compact oriented. What is it? Is its signature. And as we can already guess, the signature will be the product of the individual signatures. That's a bit harder to see, but nevertheless I can give you the idea. So let's see. The signature of the product lives on the corresponding half-dimensional cohomology of the product. So let's write a dimension of mj equals k of j. Then m1 times m2 as sorry, kj. And then m1 times m2 has dimension 4k1 plus kj. And so what we have to look at is the cohomology in degree 2 times k1 plus k2, right? So that's the cohomology that we are interested in. This is where the Poincaré bilinear form of the product manifold lives. Now in general, we have a formula for the cohomology of product manifolds. And we have discussed it in this course earlier. So what's the formula? Well, how is it called? Kunet formula, yes. And what does it say? How can I write the cohomology of a product manifold? Well, what will it possibly be? I mean, in the case of disjoint union, I got the direct sum of the cohomologies, and here I get the tensor product of the cohomologies. So I could write this like so. So this is the Kunet formula. does this explicitly look? If you have a pure tensor product represented by a form here and by a form there, you pull them back to M1 cross M2 and wedge them. This gives you a form here representing a convergent class there. So it's also the obvious map here, right? Good. And let's specialize this to this half-dimensional cohomology. Then what this tells us, so this tensor product of these forms, this is of course now a sum of tensor products of various degrees. So I can write this as the sum of HL of the first factor tensor H2k plus 1, 2 minus L of the second factor, where L ranges from 0 to the total degree here, which is k, 2k 1 plus k2. So that's just that thing spelled out in this particular case. And now we see that things are not so obvious anymore, because here we get cohomologies of all kinds of degrees here, not only half-dimensional cohomologies. But we can split the sum into one term, which is as it should be, namely where L is given as 2k1, which is the half-dimensional cohomology for M1. So let's split this term off. Tensor, and then here we have to subtract 2k1, which leaves us with 2k2. This is where our Poincaré bilinear forms for the individual factors live. And then there's the rest. Here I leave out the term where L is equal to 2k, to 2k1. And I have what I have here. Okay, and now if you look at the Poincaré duality map, I mean, it's a simple map in the end. It's given by wedging and integrating forms. Then what we see is so first of all, if I have something from here and I wedge it with something which comes from here, then this will give me 0 after integration because the degrees don't fit. So this part and that part are orthogonal with respect to the Poincaré bilinear form. And then you check, if you look at these terms by suitable interchanges of indices, that the index of the Poincaré map restricted to this part, the signature is actually 0. The signature EM1 cross M2 restricted to this part, so that has trivial signature. This is by sign counting, and so you can choose bases of these cohomologies and arrange them in such a way that you get suitable matrices for which you can read off that all the signatures cancel by writing it in terms of certain 2x2 blocks. I don't want to do that now. And here, this part is exactly, this gives me the Poincaré map of M1 tensor, the Poincaré map of M2 on this tensor product, whose signature is then just the product of the individual signatures. So the whole signature really comes only from this part of the cohomology. Maybe we'll leave it at that. And then the third property, that is still one more in the lemma, is that if my manifold M bounds a compact manifold, so if M is the boundary of some manifold W, where W is again compact with boundary and oriented. So oriented and compact with boundary. Then the signature of M vanishes. Signatures of boundaries are 0. And that is something I cannot discuss now. This is a consequence of a generalization of Poincare duality to manifolds with boundary, which is called Lefschetz duality. Follows from Lefschetz duality, which is a generalization of Poincare duality to manifolds with boundary. So this is something we have to believe now. But why am I stating this lemma? What's the reason? These 3 properties, why am I interested in exactly these 3 properties? Exactly. And it's not just a homomorphism from the core, from a cobordism group in a fixed degree. This second property also tells us that multiplication is also respected. So what we can read off from this is that, I mean, the signature is only defined on manifolds divisible by 4. I could put it equal to 0 in the other dimensions. I could do that. But I can also leave it at that and just formulate the lemma as follows. In other words, if I look at the following sub-algebra of the cobordism algebra, maybe I look only at 4k dimensional cobordisms. And here I really take also the direct sum, not the direct product, but nevertheless the direct sum is sitting in the direct product. So the whole thing sits in the direct product, and I can also get all the other degrees. So that's a sub-algebra. That is obviously a sub-algebra, because if I multiply 2 such things, I again get such a thing. And if I look at the sub-algebra, then the signature gives me now a map to integers, which, as has been pointed out by the lemma, is an algebra homomorphism. This is an algebra homomorphism. From this sub-algebra of the full cobordism algebra. Okay. Good. And now let's prove the signature theorem. Okay. So first observation. So we have the signature from this sub-algebra. So that's an algebra homomorphism. And now let's look at the right-hand side of this equation. What we have here, well, this is what? So that's a multiplicative class derived from the Pontryagin class. And so each of these terms in this class is a certain linear combination of products of Pontryagin classes. And then they get integrated over the manifold. In other words, this is a linear combination of Pontryagin numbers of the manifold. And the coefficients are somehow encoded in this power series. But each Pontryagin number is also a homomorphism. And so each linear combination is a homomorphism. So in other words, the right-hand side, just the right-hand side of the equation, is also an algebra homomorphism. And now if I want to show equality of these two things, it's sufficient to do this on a generating set on L, which generates the thing as an algebra. And we now know such one set. So suffices to show equality on a set or elements generating this algebra as an algebra. An algebra generating set. And which one do we choose? Well, we know actually a basis in each dimension here, namely the products of complex projective spaces. So in other words, the projective spaces themselves are a generating set as an algebra, because then you get all products, and if you have all products, then you get all omega 4k's, right? So this one will be such a set. So in order to show the theorem, we actually only have to check it on these particular manifolds. And that's what we do. And we simply compute both sides for these particular manifolds. Good. Let's do that. So the question is, why, or I should repeat the argument, why the right-hand side is an algebra homomorphism. And so the class that we have in here is a multiplicative class attached to the Pontryagin class with respect to some power series. And what is it? If you write this out, this means it's a certain expression in products of the individual Pontryagin classes, P1, P2, and so on. So these things get integrated over the manifold. But taking products of Pontryagin classes and integrating over the manifolds is exactly what we defined as the Pontryagin numbers. Because everything is related to the tangent bundle here. So those are the Pontryagin numbers. Therefore, the right-hand side is some linear combination with certain rational coefficients of Pontryagin numbers. Each Pontryagin number is a group homomorphism. We checked this last time, or time before last time. And therefore, each linear combination is so as well. Okay, yes, but it's a multiplicative class. So that's why it also, okay, good point. It's a multiplicative class. So if you have a product here, so maybe I should have spelled this out. Yes, it's a multiplicative class. So if you take a product here, then the tangent bundle is, as we have done in the beginning of the lecture, is up to some pullbacks. It's the sum of the tangent bundles, and the multiplicative class then splits this off as the product of the two bundles. Okay, let me write it down. I don't think we need this anymore. So this is here, yeah, that's a good question. This is why it's important that it's a multiplicative class. So if you have L of T M1 cross M2 integrated over M1 cross M2, then this is, because it's a multiplicative class, so that's the tangent bundle of M1 plus the tangent bundle of M2, and it's a multiplicative class, so we get L of T M1 times L of T M2 integrated over the product. And clearly, more specifically, it's pull back again, right? Pull back to the product. Yes. And if you integrate this over product manifold, then you have to integrate this over that, and this over that. Everything else will be 0. So that means we get L Tm1 integrated, it's a for B thing in the end, times L Tm2 integrated over M2. That's the multiplicativity. Okay? Yeah, thanks for the question. Good. All right, so what we are now left to do is to check the formula in the signature theorem for these explicit manifolds, which is good because we know a lot about these manifolds. And so the first thing I do is to compute the signature. Now, all right, so let's see. If I have CP to M here, and what is its signature? So I have to look at the cohomology, 2m dimensional cohomology of CP2M. The real dimension of that thing is 4m, or let me call it 4k to be consistent with the previous notation. We are on omega 4k here. So that cohomology, we know the cohomology of complex projective spaces. Namely, this is spanned by the corresponding power of this generator. So that is a to the k and all multiples of it. It's one dimensional. And so the Poincaré bilinear form is really given by a 1 cross times 1 matrix in this case. And what is it? Well, so the Poincaré bilinear form of CP2K, if I apply it to this generator, again, this generator, there's nothing else I can do. This means I have to take the product of the two and integrate it on the manifold. So that is, of course, just A2K integrated on the manifold. And we know that this gives us 1. So it's the 1 cross times 1 matrix with the entry 1. That's the Poincaré bilinear form, so the signature is equal to 1. Signature of CP2K is equal to 1. Alright, so that was easy. And now we have to compute this strange term given by this power series. And let's see what we get there. Alright. Now, let's recall the Poincaré, let's recall the Pontryagin class of the tangent bundle of CP2K. What is it? We have computed it. So it's given by 1 plus a squared to the dimension 2k plus 1. So that's the Pontryagin class. Aha. But we don't need the Pontryagin class, we need this L class. So what is that? And remember the recipe for multiplicative classes, if you have something which is symmetric in linear factors, then you take these factors, like here, and then you take these factors, put them in the power series, and multiply them, right? So the general rule would be if the algebraic recipe is such that if you can write P as 1 plus lambda 1 all the way up to 1 plus some lambda k, then the corresponding L class would be take these lambdas, insert them into the power series and multiply those. So that's the recipe. So in our case, we substitute all of these lambdas equal to a squared. So what we have to do really is we have to put in a squared in this power series little l that defines the class. And then we have to raise this to the 2k plus first power. Because that's the number of factors. Okay, so let's see. So you see already this a squared will simply cancel the square root. So what we have is a on hyperbolic tangent of a, and the whole thing to the 2k plus first power. That's the class, the homology class. But then we want to integrate against the over the manifold, and what will happen then? Well, integrating over the manifold will single out, so that's some power series in A, and it will single out the coefficient of degree 2k. Yeah. So what we have to find is, in this power series here, we have to find the coefficient of degree of a to the 2k. Don't need this anymore. So, okay. Write it down. Integrating this. So this is okay, CP2k. Integrating it over CP2k. So that's the coefficient of a to the 2k, because that's what integrates to 1 in this expression. How can we do such a thing? If we are given some complicated power series, how can we find a certain coefficient in that power series? And let me write down the power series once more. Now I replace the homology class A by a generic complex variable. It doesn't change anything really, because we are just looking for a certain coefficient in the power series. So I could rephrase the question. If I look at this simply as a complex power series, what's the coefficient of z to the 2k in that power series? That's what's interesting me. And well, in complex analysis, you learn a trick, namely, if you look at the Laurent series, there's a way to single out the term in front of z to the minus 1. That's called the residue. And there's a residue theorem telling you how to compute that, namely by taking the Laurent series and integrating around the origin once and divide by 2 pi I. That's the residue theorem. Now here, this is not that's a power series, it's not a Laurent series, and we are looking for the coefficient of z to the 2k and not for the coefficient of z to the minus 1. But let's just divide by a suitable power of z so that the coefficient we are looking for becomes the residue. And so for this, we just have to divide by z to the 2k plus 1. Now the coefficient of z to the 2k after this division is the coefficient of z to the minus 1. And then that's the residue. And in order to obtain the residue, I can integrate this over a loop gamma, which goes around the origin in the complex plane in the mathematically positive sense on the origin, and I have to divide by 2 pi. So this coefficient here is equal to this expression, dz. So that's the residue theorem. All right, that's good. That's actually pretty good, because this z that I had to divide out here exactly cancels that z. So I can simplify this somewhat. So I get then z divided by hyperbolic tangent z to the power 2k plus 1. So that's what we want to compute. And in order to do that, there's now a natural thing to proceed. Well, there's this tangent hyperbolic in the denominator looks complicated, so let's get rid of it by a suitable substitution. So let's substitute u equals tangent hyperbolic of z. It's a holomorphic transformation. I can do that, and the origin gets mapped to the origin. So I can equally well, after this substitution, apply this to the corresponding transformed Laurent series. So let's see du, make the substitution du and dz. This is the derivative of that tangent hyperbolic, so that's sine, hyperbolic sine divided by hyperbolic cosine. So if I differentiate this, I get cos squared in the denominator, and in the numerator I have sinh differentiated gives cos times the numerator squared minus, then I have the numerator sinh times the denominator differentiated, which is b squared here. So we see what we should have known in the beginning. This gives me minus tangent hyperbolic tangent squared. And in other words, this gives me 1 minus u squared. So if I now solve for dz, which I have to replace here, then I see dz, and this on the other side, and this is du divided by 1 minus u squared. Okay, so I can go in the formula here with the substitution, and then I have du divided by 1 minus u squared, and then I have also these terms here, namely this is u to the 2 k plus 1. So now that's much easier because I can simply expand this in a geometric series. So I do this. So I'm just expanding 1 minus u squared in a geometric series. Then this gives me 1 plus u squared squared equals power 6 power and so on. And this I leave unchanged. Du. And now we see we can go back, because now I'm looking at the residue of this Laurent series. So I'm looking for the coefficient of u to the minus 1 in this Laurent series, which is the same thing as the coefficient of the term u to the 2k in the numerator. So that's the and all the coefficients in this series up there are plus 1, and so and that's the same thing that we got here, and that concludes the proof. So that is more or less Hirzebruch's original proof of the signature theorem. Nowadays there's a different approach based on index theory, which has also its merits. But if you do the index theoretic approach, then you first have to relate the signature to the index of a certain operator. And we didn't have to do this here. We work directly with the signature and some of its invariance properties. And so in a way, this is a rather direct proof. And that's an interesting method to see how this works by using these invariance properties of the signature as well of the multiplicative numbers, so that one has to check it only on a certain set of manifolds where one can do explicit computations. Last time there was a question asked, to what extent are the oriented cobordism groups known? We know them in dimensions divisible by 4. They are free and generated by these products of complex projective spaces. They are known in all dimensions nowadays, and the history is more or less like this. René Thom, who we have mentioned earlier, he computed the cobordism modulo torsion. And then CTC Wall proved that the only torsion that can occur is two torsion. We had a brief discussion about this last time. This comes from manifolds which have orientation reversing the diffeomorphisms. And that's the only thing that can happen and lead to torsion elements. And then Ball also computed the complete cobordism algebra by proving that two manifolds represent the same cobordism class if and only if all Pontryagin numbers coincide and all Stiefel-Whitney numbers coincide, which we haven't discussed yet. So that's actually if and only if relation. And from this, one can read off the complete cobordism, so it's completely fine. All right, any questions? Yeah, it's the so-called signature operator, and it's in fact similar to the Euler operator that you would use for the Gauss-Bonnet theorem. So it's really the operator on differential forms. It's not, I mean, it's pretty obvious that you have to do something on differential forms because the signature is defined on this homology, which relates to differential forms. So what you look at is the operator d plus d star, so exterior differentiation plus its adjoint with respect to some metric. So if you choose a metric on the manifold first, we have to do that here. And for the Euler operator, for the Gauss-Bonnet theorem, you would split this operator into one that takes even forms to odd forms. And for the signature theorem, you take the same operator in principle, but you look at a different splitting, which is related to this half-dimensional homology. So operator is in principle the same in both cases, but the splittings are different. Any further questions? I've never asked Hirzebruch how he found this function. No idea. But I do know in this 1950s when this was, early 1960s when this was developed, and before the Atiyah-Singer index theorem was found, that they played a lot with all kinds of different power series and these things. But how they finally found them, I have no idea. Well, there are lots of different proofs of Atiyah-Singer, of course. And the K-theoretic proof is similar in the sense that you look at certain invariance properties. In that case, you look at the topological and analytic index and you show that they have certain transformation rules and that they coincide on certain generators. So in that sense, the philosophy is the same. And I'm pretty sure that they were inspired by this kind of proof. So historically, Hirzebruch's proof was earlier. Certainly, I would think so. And also, the cobordism theory and the K-theory were pretty new at the time. So people were very aware of these new structures. And I would guess that one of the reasons why they put so much effort into developing cobordism theory and K-theory was exactly in order to prove that sort of thing, like the Atiyah-Singer index theorem. So I mean, all these people who have done it are dead by now, so it's impossible to ask them. But I would think that probably the K-theoretic proof was inspired by these ideas which were available from Hirzebruch, for instance. Yeah. But of course, now we have also proofs of the Atiyah-Singer index theorem which are completely different. Okay, thank you.